This video is for assignment number 7 on trig substitution as an integral technique. So I wrote out some common things that are good for you to remember from trigonometry and the calculus of trigonometry. So this is some basic geometry with the opposite, adjacent, and hypotenuse, and defining sine, cosine, and tangent, cosecant, secant, and cotangent, and then also the trig derivatives that you should be familiar with. So I think it's best to do this topic by example. So let's look at this first example, and then eventually we'll stop and look at some kind of formula types set up for them. So the first example is the integral of 1 over x squared square root of 9 minus x squared dx. And we want to try to use a trig function to help in a substitution technique. So it's basically similar to a u substitution, but you might refer to it as a theta substitution or a trig substitution. And the reason that it works is because this square root expression is actually a common situation that will come up from the Pythagorean theorem on a right triangle. So imagine that you ended up having this as one of the sides of a right triangle, and then what would the other sides have to be? So I'm not explaining that very well, it'll help after you see it. So for example, if the hypotenuse had 3 on it, and this opposite leg compared to theta had x on it, then how long would this adjacent side be? And it works out that if you do the Pythagorean theorem with 3 squared is equal to x squared minus this side squared, or plus this side squared, and then you solve for x, or you solve for this missing side, you'll get that 9 minus x squared is equal to this side. So having that set up makes it so you can take advantage of this triangle and the trigonometry for it for a substitution into this. So one thing that will be particularly helpful on this problem is to write down the fact that sine theta is equal to x over 3, or x is equal to 3 sine theta. And that's just using the concept of the opposite over the hypotenuse is equal to the sine function. And then that is an easy function to take the derivative of. So the derivative of x is dx, and the derivative of 3 sine theta is 3 cosine theta, d theta. So that gives me a substitution if I'm trying to change the variables in this integrand to be thetas instead of x's. I've got something I can put in for the dx. And I want to have some way to replace this square root in terms of theta. What comes to mind here is that I could say a trig function of theta is equal to this side over the hypotenuse, or the adjacent over the opposite. I'd rather use the one with a constant in it, so I'm going to use cosine of theta and say that that's equal to the square root of 9 minus x squared over 3. And so I can say that 3 cosine theta is equal to the square root of 9 minus x squared. And so as I go to put in this substitution, right now I can take out this and put in 3 cosine theta, and I can take out the dx and put in 3 cosine theta d theta, and then I still need something to put in for the x squared, so I'll need to figure out something that is equal to x. But I've got that already here. X is equal to the 3 sine theta, and so I can take out the x and put in 3 sine theta. So the 1 is going to stay 1. The x is going to become 3 sine theta squared. The square root of 9 minus x squared is 3 cosine theta. And the dx is 3 cosine theta d theta. And so this works out nicely because this turns into the integral, and the 3's can cancel. That is a 1/9, and it's 1 over sine squared theta d theta, which really know the antiderivative of that in that form, but keep in mind that 1 over sine squared is equal to cosecant, oh my goodness, 1/9, the integral cosecant squared theta d theta, and the antiderivative of cosecant squared is negative cotangent. Plus c. So you might think that you're done here, but the problem as it is right now is a function in terms of theta, and this is an integrand in terms of x, so somehow you've got to go back and do one more trig step here to get back in terms of the x's. So it's saying cotangent theta here, so look at this, and the tangent, hopefully you remember easily, the tangent is the opposite over the adjacent, and so the cotangent is the adjacent over the opposite. So then I can substitute in the square root of 9 minus x squared over x plus c. So if you take the derivative of this function, you should get that function. And I'm not going to take the time to show it right now, but you could stop the video and try that. All right, I'm going to get one more example in this video, and there we go. So example 2 is the integral of 1 over the square root of 4x squared plus 1 dx. All right, so it's always a good idea when you're learning a new technique to stop and make sure that there isn't another way that you would know how to do this problem. So if you were just trying a u substitution, you could say, well, u equals 4x squared plus 1, and then du would equal 8x. So if this had been a 1x on top, then a u substitution would be a good option. It's not set up to be something like an integration by parts. Remember, an integration by parts problem is one that kind of looks like this, is a good classic integration by parts, where this one gets easier when you take the derivative of it, and this stays about the same when you integrate it. And so it's a good setup for an integration by parts. So anyway, if you kept trying to do this, you would run into trouble trying to get your answer to it. So we're going to use a trig substitution, and I recognize it as a trig substitution problem because it has the square root of a quantity that can be the sides of a triangle here. So try to figure out, and you could pause the video here, what the side lengths of the triangle would be in order for this to be the expression on one of the sides. It can be on the leg or the hypotenuse. And there's a good indication of which one it should be. This plus tells you that. All right, so hopefully you had a chance to think about it. The way that this one works is if you have a 2x here and a 1 here, then the hypotenuse will equal to 4x squared plus 1 square root of that. Now, it doesn't make too much of a difference which one you put the 2x and the 1 on, except for that, keep in mind that you're going to write a trig function that avoids this square root in it, and so in this case I would want to use the legs, and so my choice is to use tangent or cotangent, and the derivative of tangent is secant squared, and the derivative of cotangent is negative cosecant squared. And so everyone always will put this such that you would want to use tangent, and tangent's better because the derivative doesn't have a negative in it, and when you do the tangent function, you would want, whenever you pick this, you want the x to be in the numerator of your trig function because it's easier to differentiate. So when I do 2x over 1 here, both of these are easy to differentiate comparatively to if you had switched it around and had the triangle with a 2x and a 1, and then you set up the fact that, say, tan theta is equal to 1 over 2x. Well, then you have tan theta equals 1/2 x to the negative 1, and your derivative ends up having an x to the negative 2 in it, and then suddenly the trig substitution just isn't helpful. So we're going to stick with this, and then the whole reason we need this is we need a way to replace the dx. So I'm going to write an equation that has an x and a theta in it, take the derivative of both sides, and I'll have a substitution for the dx, and then we'll worry about the other pieces later. So the derivative of tangent is secant squared theta d theta, and the derivative of 2x is just 2 dx. And so this can be 1/2 secant squared theta d theta and dx. All right, so that will replace the dx. And then just look around at the picture. There's some options here, but what stands out to me is that this whole integrand is 1 over root 4 x squared plus 1, and that is right here, 1 over root 4 x squared plus 1. And what function would take the adjacent over the hypotenuse? So I can get this cleaned up, switched around in a nice efficient manner here. 1 over cosine of theta is equal to that. So this whole integrand can just be replaced with cosine theta, and the d theta can get replaced with 1/2 secant squared theta. So that's cosine theta, and the dx is 1/2 secant squared theta d theta. And we just want to simplify that expression, and so it will become cosine theta on the top, or 1/2. Secant squared is 1 over cosine squared, and so this becomes the integral of 1 over cosine theta, which is the integral of secant theta d theta. Now that's kind of a bummer because a lot of students probably don't have the antiderivative of secant theta memorized, but if you were about to take a test on integration, it would just be one of the ones you would want to brush up on. So I'm not going to take the time to give a derivation of that, but the antiderivative of secant theta is the natural log of secant theta plus tangent theta. If you looked at a table of integrals in the front cover of a calculus book, this one would be on the list. All right, and then you're not quite done yet because this function has thetas in it, and you need to go all the way back to x's. So one last step. The secant of theta is equal to the reciprocal of cosine. So instead of 1 over this, it'll be this over 1. So So secant of theta is just 4x squared plus 1, and the tangent of theta is the opposite over the adjacent, which is 2x over 1, or just 2x. Alright, so that is the solution to the second example, and I'm going to do a different video for the third example just so YouTube doesn't reach its maximum time.